Hello and welcome back. We're gonna start chapter 2, where we're gonna talk about sets. Now, we tend to think of mathematics because we're taught from an arithmetic standpoint of being numbers, and I think the modern concept of mathematics is going to be sets. Now, we have cultures have learned mathematics through number. And only recently have we looked at number as being a part of kind of a more general idea of pattern. And we look at pattern through sets. And so we've already been exposed to some sets. We have natural numbers, the set of natural numbers, which is the collection of counting numbers. 1, 2, 3, up to infinity. We'll find out that we have whole numbers, which is the natural numbers plus 0. And we'll see that historically not all cultures accept the concept of 0. The Greeks thought that nothing was something, so you couldn't have nothing. So they didn't really quite accept the idea of 0. Try saying that one fast. And then we have integers, where we can have negative numbers. And positive numbers, and so on. And we'll work on defining sets of numbers. But I think to really start a good talk about mathematics, we're going to have to talk about what sets are and what it means to have a set of things. And so we're going to define sets and have some different ways of talking about them. And so sets are collections of objects. And I'm going to use the book definition, whose contents can clearly be determined. And so when we say clearly being determined, what we're saying, is that there is some pattern that defines the objects. And one of the things we'll see, and there's a lot of study into what it means to make objects out of the world. And once you have objects and you think in terms of the objects and the patterns that relate the objects, you change the way you think. We are not born seeing distinct things within the world. We learn distinct things. Even anthropologically, we develop language in different ways. There's a beautiful thing on color theory where we learn different colors historically at different times, and without having the word for the color, our ability to perceive the color is different, which means that we interact with things differently. And numbers are the same way. Having the objects and the object definitions that become in sets of numbers, we start thinking in the patterns that come along with having these words and the whole syntax and language that goes with them. And so our job here is going to be to look at how we collect objects together. Now, sets are going to be made of elements. And so elements are the members of the set, or the objects themselves. And a set is well defined if the elements can clearly be determined. Right, if we can see the pattern that is going into the set. The order that we put the sets isn't really that important. And repetition may or may not have meaning in a set. In general, we name sets with capital letters for our variables. So I could say the set W, and I'd write it big. And this could be a set that contains words. It could be a set of famous books about whales, right? It could be the days of the week. And so let's make W be, days of the week. And we're going to use a roster method. And what we mean by a roster is I write every member of the set out. Right, it's like a roster, like a roll call. And so in this roster method, notice a couple things I did. I put curly braces to enclose my set. I list each and every element, and I separate them by commas. And so this is well defined. I have the set that's the days of the week, and I can see each element. And the definition of the element goes in there. And so we use those braces to enclose the set and the commas to separate the elements. And so we use this roster method to write the days of the week. Now this is good for small finite sets, right? Days of the week, there's only 7 of them, and you'll see some examples in the slides where name all the coins, and so you've got like quarter, $50, penny, nickel. They're things that there is a limited amount of, and so we can fit them all on a piece of paper. We can fit them all within braces. But sometimes the thing we want to make a set of, we can't list on a piece of paper. It's going to be too hard to write all of the things down. There might be more elements than fit. Or what's more important is the pattern that creates the elements. And so what we're going to do is we're going to extend our roster notation. We're going to move to set builder notation. And so in set builder notation, we're going to have a place for the elements of the set. So let's say W equals, and then I'm going to have in it, I'm going to declare some variable. For now, I'm going to use X as a variable. I'm going to put a pipe, and then I'm going to put a rule. Now, again, I'm following the book's example right now. I think we'll do another example as we continue on. And so we're going to read this as the set W, and then equal sign is going to be is, and this is starting a set, so I'll say the set the set of, I guess. And then this would be all elements X, and then the pipe will say such that an element X is the day of a week. And so we've introduced a couple of ideas here. One of the things that we're going to do in mathematics a lot is we're going to take a large section of words and encapsulate them in a symbol. This is just a way of being able to talk about these abstract concepts in less paper. I always say mathematicians are lazy. We don't want to write as much, and so we come up with symbols that translate back into sentences. And the sentences will eventually translate in our minds for the concepts that they are representing. And so large capital letter is the set. Equal sign is usually an is, or like, we'll have different words around, but it's usually is or are. Braces tell me I'm doing a set. This names the element, and then the pipe is such that, and then I have the rule that I'm going to follow. And this lets us generalize some things. Let me look. I'm going to jump a little bit ahead mentally for us. I'm going to introduce some set builder notation that's useful from a numeric sense, and then we'll drop back into some generic. So I can say O is the set. And so what I'm going to do here is I'm going to say this is going to be odd numbers. And I want to say that it's the set of all elements x such that x equals 2n plus 1, where n is an integer. Now, what I've done here is there's an infinite amount of odd numbers. Right? 1, 3, 5, 7, -1, -3, and so on. And this set builder notation lets me create a rule to talk about just odd numbers. Because if I take any integer, and I'll take just the positive ones right now, 1, 2, 3, 4, 5, and I plug it into this rule, so I'll take 2, and I'll plug it in. 2 times 2 is 4, plus 1 is 5. That's odd. Plug in 1, 2 times 1 plus 1, so 2 plus 1, 3 is odd. And we'll find that this notation lets me talk about odds. In fact, I could say even is the set of all x such that x equals 2n, where n is in integers. And we'll find more words for these as we go on. Right now, what I'm showing is the utility of set builder notation, that we can talk about an infinite amount of things with how I create the thing. We'll focus on words a lot now as we get comfortable with it. But what I wanted to show us is where this tool is going to take us. It's going to take us from being able to talk about quantity and talk about infinite amount of things in very short symbols. Well, one of the things we have to be able to do, whoops, I'll scroll down here, sorry about that, is talk about probably one of the more confusing aspects of sets, which is what happens when I don't have anything at all. And so we write the empty set as a 0 like with a line through it. And this is the empty set. And this is equal to a set that has no elements. It contains nothing. And it's also called the null set. And so this is the empty or null set. Oddly enough, I can make a set of sets, and this set is not empty because it contains the null set. And some of these type of paradox ways of talking we'll have to work with. But the null set is the same as a set that has no elements, where the set of the null set, that's not empty. Chew on it. It still confuses me, but it does become useful to be able to talk about nothing and talk about nothing as a something. It goes back to the Greek saying that nothing is something, so you can't have nothing. But we're going to recognize it in sets. All right, so I introduced this notation a little bit ahead of time, but what we're going to have is this, which can sometimes be read as in, or member of, or element of. And it's kind of like a curved E. And so when I said x was a member of or is in the set of integers, this tells me this element is a member of this set. And if I'm not a member of a set, I strike it out. And I say X is not an integer. And so we get the ability to say not an element of or is an element of. So I can make a set notation and talk about elements in it. So one last touch. So I can talk about lowercase letters, and I can write them in a roster notation where the ... says, hey, you've seen this pattern before, you know what comes in the middle. And I can say then that R is an element of all the lowercase letters. The ... notation is good to save space if we can clearly define the set. And so we have to look at this and go, well, yeah, I guess this would be all the letters in it. And so if it's vague and the ... dot's in there, we will go to set builder notation. Well, I can also say that capital R is not a member of lowercase letters, or is not an element of. And so R is an element of lowercase letters. So lowercase r is a member of lowercase letters, and capital R is not an element of lowercase letters. And notice I keep switching member of and element of. Your book's going to use element. I've used membership in my language a little bit in how I talk about sets. I try to keep the book terms together, and we have this in mathematics, as we have some different terms that get used in different subfields. All right, I'm going to clear this page here, and we're going to look at some sets of numbers, which I've already talked about in the general term, but we'll get some specifics coming up. And so we get represented by a very bold N, or when we sometimes write it, we'll double strike it, is going to be the set of natural numbers. And there's some debate on natural numbers and whole numbers. Where do they start with? But we're going to take the idea that these are also called the counting numbers. And I'll put dots, and they go off towards infinity. And so that's the set of natural numbers. And those three dots mean, hey, this is going to go on forever. Well, we can represent parts of natural numbers. So I can say A is equal to 1, 2, 3, 4. Or I could write this in set builder notation. I could say A is the set of all x such that x is a member of natural numbers and x is less than 5. And that gives us A. And so when we do set builder notation, we're going to can use inequality and equality symbols to help us talk about how our numbers come together. So I could do another set. B is the set of all x such that x is a member of natural numbers and x is less than or equal to 5. And so we're going to have less than or equal to. And so B in roster notation would also contain 5. And so notice the difference. Without the equal bar underneath it, I get everything up to but not including 5. With the equal bar to it, I get everything up to and including 5. see here. And we can also have the other boundary. So I could say C is the is the set of all x such that x is an element of natural numbers. I'll do my double strike there. And x is greater than 5. Which that means C is going to start at 6 and go on up to infinity. And so this is greater than, and this will be greater than or equal to. Sorry, my handwriting, the way my tablet gets off there on the side, I'm bumping into the keys. Sorry about that. And so, if you're on a blackboard, I'd be doing this covered in chalk, right? In class, in person. And so we'll do an element D is the elements is all x such that x is an element of natural numbers and x is greater than or equal to 5. And so D would start with 5 and continue on out towards infinity. And so this lets us be able to talk about infinite things in a very compact space. Well, I'm also going to be able to talk about finite things in a compact space by wedging things within boundaries. So if we think about what these sets are doing, if I draw I'm going to draw a number line here, and I'm just going to look at D here, where I had 5, and I had all the stuff bigger than 5. I could color everything here and just keep on going down the line. And so this talks about a boundary, and that boundary is 5, and I have 5 because it has this equal sign. Well, I can also talk about all the numbers in between two numbers. And I can do that by using two inequalities. Two inequality symbols. So I'm just going to keep renaming my sets here as I go through. So we're going to say E is the set of all x such that x is an element of natural numbers and 5 is less than x, which is less than 9. And so E doesn't have 5 on its lower boundary. And notice the lower side, this points towards the small things. And so I'll have 6, 7, and 8, but I won't have 9. And so my set, or elements, is wedged between 5 and 9, not including 5 and 9. And of course I can do odd things. I could have 5 on my one side, but not 9, and so on. The equal tells me if I have this, or if I'm less than that. And so we can use inequalities as a way of representing sets and representing our sets out of these natural numbers or any other numbers that we have. Right, and so we're collecting things, we're collecting objects, we're collecting numbers, and we're having notation to let us build these. And notice we've brought around collections of things and from words and names of the week, and there's going to be some examples in the lecture slides that do different types of collections things. But now we're talking about numbers and how we collect numbers together. And we have our natural numbers. A kind of hidden thing that I want to say in natural numbers, just so we look for patterns, is what makes this set what it is and why it's counting numbers is it starts. It has a starting place. And so it starts at 1. And there's a pattern to this. I can only do one thing. I can add 1. And that gives me my next element. And so we can build natural numbers with only the concept of the number 1. And it represents putting tick marks down. I either don't have any tick marks, so it's an empty set, or I start with a tick mark, I get another one that gives me the next number. And so natural numbers map back to our idea of counting. That's why we kind of say they're the counting numbers. And it has a simplified rule set. I have this idea of 1, and I can add 1 to things, and I get my new names. Now, what we want to do is talk about how we can start saying if sets are equal to each other or not. And so one of the first things we're going to measure is the cardinality of a set. And we do this by talking about a set's cardinal number. So a set has a cardinal number. And we write this by saying n parenthesis set A. And so this is the cardinal number of set A. So we write it like this. And what the cardinal number is it's the number of distinct elements in a set. So repeating elements does not add to the cardinality. So I'll make a simple example. And so we read this as n of A. And so if I had A equal 1, 1, 2, 3, n of A is going to be 3. There are 3 distinct elements. Even though I've repeated 1 twice, there are 3 distinct elements, 1, 2, and 3, that they're distinguishable from each other. And so cardinality is a way of talking about the size of the set in distinct elements. Well, if we have cardinality, then we can start talking about the idea of equivalent. I never get my spelling right on this. Yeah. Equivalent sets. And what we mean by equivalent is the n of set A is the same as the n of set B, or the cardinal number of A is the same as the cardinal number of B. And so they have the sets are equivalent if they have the same cardinal numbers. And this is going to be really important for us mathematically because it lets us do things we call mapping. And so I'm going to draw just a fuzzy representation. Sometimes we can draw sets as like collections out in space. And if I have the same number of elements, 1, 2, 3, 4, 1, 2, 3, 4, and X, Q, smiley face, left, right arrow, right? These are my elements in the set, X, Q, smiley face, left, right arrow. And so this is set A, and there are 4 elements. So n of A equals 4, and we'll call this set B, and we'll say this is 1, 2, 3, 4. And n of B is also 4. And so I can map. I can say that I can represent these elements by one or the other. When we have the same cardinality, we're going to be able to talk about sets in a similar way. But these sets aren't equal. Right? Equivalent sets have the same number of elements, but they don't. The elements do not have to equal each other, and we call this a one-to-one correspondence, because one thing to one thing, and one thing back to one thing. So 1-to-1 correspondence. One-to-one correspondence happens when sets have the same cardinal numbers. And I'm just going to write that in our notation now. And if we can't place them into one-to-one correspondence, then they're not equivalent. Oh, I filled another page here. This will be my last page. I'll do one more set of notes on this first little bit of lecture material. Now, we have two types of sets, and I've already alluded at them, right? We did natural numbers, and they start with 1, but I had to use the dot dot dots because my rule for these is start with 1 and then add 1 to it. Well, I can add 1 forever, right? So it's infinite. And so this is an infinite set. And what's neat about infinite sets is I can still talk about them. Collecting them and using sets as a way of putting them together and focusing on the pattern, I can still talk about sets. Now, if A contains elements, then it's finite. Contains elements that are bounded, right? Doesn't repeat forever. I mean, there's a pattern that creates these, but it has a definite beginning and a definite end, and that's finite. And the last thing we want to do in this idea of defining our sets is we can have equal sets. Oops, let me change my colors. And so for sets to be equal, we need their cardinality to be equal, but then we also need, and we'll write equal sets as A, the set of A is equal to the set of B. They're going to have the same cardinality, but then they also have the exact same number of elements. So if A is the 0, 1, 2, and B is 1, 0, 2, then I can say A is equal to B. They have the same cardinality and the same exact elements. If C is 1, 4, 5, they have the same cardinality, but they don't have the same, and so A is not equal to C. And so that'll be our extra notation, is equal and not equal. All right, this is the video for Chapter 2, Section 1. Play around with the homework, and let me know if you have any questions.